Module 1 Operational Amplifier Lecture 2. In this session, we'll be learning about the applications of op-amp with negative feedback. We have linear applications of op-amp and non-linear applications of op-amp. Linear applications of op-amp. Here, the output is directly proportional to the input, which means that if there is increase in the input, there is increase in the output too. Example: inverting amplifier, non-inverting amplifier, summing amplifier, difference amplifier, etc. Non-linear applications of op-amp. Here, the output is not directly proportional to the input, which means the output is inversely proportional to the input. It states if there is increase in the input, the output decreases, and vice versa. Example: integrator, differentiator, logarithmic amplifier, etc. Now, before going in detail about the linear applications and the non-linear applications, we'll be learning about the virtual ground concept, or it is also called as virtual short circuit. Now, have a look at the circuit. So, we have an ideal op-amp with input resistor and the feedback resistor. The notations are given below the circuit. Vi is input voltage, V0 is output voltage, II is input current, IF is feedback current. For better clarification, IF is current through the feedback resistor RF. VB is the voltage at non-inverting terminal. RF is feedback resistor. RI is input resistor. VA is voltage at inverting terminal. So here, to be clear about inverting and non-inverting, you can see the negative terminal is your inverting terminal and the positive terminal is your non-inverting terminal. And you can see here two terminals A and B. So the voltage at your terminal A is VA. So it is called as voltage at inverting terminal. And your voltage at B, the terminal B, will be your VB. So it is called voltage at non-inverting terminal. You can note down that we only deal with the ideal op-amps, whereas the practical op-amps are not used in the theory sessions. Now, for an ideal op-amp, the open loop gain A will be equal to infinity and the input impedance Zi will be equal to infinity. You can see a statement over there. Even though the inverting terminal is not grounded, there exists a virtual ground as far as the voltage is concerned. Now you can observe a circuit diagram at the corner of the slide. We have an ideal op-amp with input resistor Ri and the feedback resistor Rf. Here, the non-inverting terminal is being grounded, whereas your inverting terminal is being applied to an input voltage Vi. As the non-inverting terminal is being grounded, the voltage at the terminal B, that is your VB, will be equal to 0. You can note down that. And at the terminal A, it acts as there exists a virtual ground. So the voltage at the terminal A, that is your VA, will also be equal to 0. Now, there's a small derivation part. You can observe that and note down. So, we have open loop gain A is equal to V0 by VB minus VA. This is nothing but the output voltage to the input voltage. Output voltage is V0. To the input voltage, we have VB and VA, two terminal voltages. So, we can write it as VB minus VA, which is equal to infinity, which we already know from the condition. Now, VB minus VA is equal to 0, which implies VA is equal to VB. We already know that based on the virtual ground concept, your terminal voltage at B, that is VB, is equal to 0, which implies VA is also equal to 0. And you can note down one more thing. As your input impedance is infinity, the current through the op amp. So after the terminal A, there will be a current flow through the op amp. Even that current will be equal to 0. So that's all about the virtual ground concept. Now coming to the inverting amplifier. An amplifier whose output is 180 degree out of phase with respect to the input is known as an inverting amplifier. Now to satisfy this statement, we have the input and output waveforms. You can observe that the input waveform, we have a sinusoidal signal at the input, the same thing at the output, but at the output the waveform has a phase reversal of 180 degree with an amplified version. Now the circuit diagram. Have a look at the circuit. Now the circuit, it is an ideal op amp with input resistance Ri and the feedback resistor Rf along with the respective currents flowing through that. And as I said in the previous thing, we have a current flowing through the op amp that I have considered it as IB. We can consider it as anything like IA or either IB. Now coming to the derivation part, you can note down one thing before going in detail about the derivation. The input signal Vi is applied to the inverting terminal of the op amp through a resistor Ri. The non-inverting terminal is grounded. Rf is the feedback resistor connected between the output and the inverting terminal of the op amp. Now, by applying KCL at A, that you can refer the circuit diagram at the corner of the slide. So by applying KCL at A, that means applying the Kirchhoff's current law. We already know that the KCL states that number of currents entering at a point is equal to the number of currents leaving at the point. So II is equal to IB plus IF will be your equation number 1. So II is your entering current at the node A, and which is equal to IB plus IF. IB and IF are your leaving currents. Now we already know that the current through the op amp will be equal to 0. So your IB will be equal to 0. Now by substituting IB is equals to 0, your equation 1 becomes II is equal to IF. Further, this II can be written as Vi minus Va by Ri is equal to Va minus V0 by Rf. We already know that based on the virtual ground concept, your Va is equal to 0. Now by substituting Va as 0, we get Vi minus 0 by Ri is equal to 0 minus V0 by Rf, which implies Vi by Ri is equal to minus V0 by Rf. Now we only need the output voltage. So to get the output voltage, segregate all these apart. So you get V0 is equal to minus Rf by Ri into Vi. So you can note this. Your output voltage is equal to minus Rf by Ri into Vi. Now to get the gain expression from the output voltage. So gain expression, we already know that A is equal to its output to the input. So your output voltage by input voltage will be equal to minus Rf by Ri. So this is about the derivation. Non-inverting amplifier. An amplifier whose output is in phase with the input is called the non-inverting amplifier. To satisfy that statement, you can see the input and output waveforms at the figure 1. Now don't get confused between these two figures, both are same. I'll explain you that. Now look at the input and output waveforms. So as you can see that there is an input sinusoidal signal at the terminal B. So here the input is connected to the non-inverting terminal, and at the output your waveform is amplified, but there is no phase reversal or phase shift exists. It's in phase with the input waveform. Now the circuit, if you look, we have an input resistor Ri and then feedback resistor Rf. It's a simple basic ideal op amp, but the thing is here the non-inverting terminal is being given to the input voltage and your inverting terminal is being grounded. Now if you observe the figure number 2, it's same as the first figure number 1. So you can observe here the non-inverting terminal has been given to the input voltage Vi, and we have two resistors here R1 and R2. Your non-inverting input terminal has been grounded, and your R1 here in the second figure is nothing but your feedback resistor, and your R2 is nothing but your input resistor. So and the current flowing through those resistors will be same, and we have an output. Now coming to the derivation part. Before going to the derivation part, note down one thing. The input signal Vi is applied to the non-inverting terminal of the op amp, whereas the inverting terminal is being grounded, and the resistor Rf, that is the feedback resistor, is connected between the inverting terminal and the output terminal. Now by applying KCL at node A, so your first equation will be II will be equal to IB plus IF. Now we already know that the current flowing through the op amp is 0. So by substituting IB is equal to 0, we get II is equal to IF. And we know that the current II is flowing through the resistor Ri. Therefore your II can be written as, the ground voltage is 0. So 0 minus Va by Ri is equal to Va minus V0 by Rf. Now observe carefully, and Va is equal to Vi. We mentioned that because if you observe the terminal, at the terminal B we have an voltage Vi. Based on the virtual concept, we can consider the terminal voltage at Va is Vi. So therefore by considering Va is equal to Vi, replacing it with Vi, we get minus Vi by Ri is equal to Vi minus V0 by Rf. Now segregating voltage and the input voltage apart, we get V0 by Rf is equal to Vi by Rf plus Vi by Ri. Now in the next step, V0 is equal to, so this Rf will be sent that side. So Rf into Vi by Rf plus V0 by Ri. Now by taking common out, that is your Vi will be taken out. So by taking out, we get V0 is equal to Vi plus 1 plus Rf by Ri. That is your output voltage. You can note down that. And to get the gain expression from this, your gain will be equal to V0 by Vi is equal to 1 plus Rf by Ri. So this is about the derivation part of non-inverting amplifier. Op amp as voltage follower. An amplifier whose output follows the input is known as voltage follower. Look at the circuit diagram. Here the inverting terminal of the op amp is shorted to the voltage terminal, and whereas the input voltage is applied to the non-inverting terminal. Now a voltage follower is obtained from the non-inverting amplifier by shorting Rf. The function of the circuit remains same with or without the input resistor. The output is fed back directly to the inverting input terminal. Since voltage gain is unity, there is no phase shift between input and output. Therefore, it is called as buffer amplifier. Now we have a small derivation here. You can see V0 is equal to Vi plus 1 plus Rf by Ri. So this is the output equation for the non-inverting amplifier. So as we have given the input voltage to the non-inverting terminal, your output equation will be this. Now we already know that there is no resistors here, it's been shorted, so your resistor value will be 0. So by substituting your resistor value as 0, we get V0 is equal to Vi into 1 plus 0, which implies V0 is equal to Vi. Now from this your gain will be 1. So here we come to the end of the session. Thank you for watching.